Hi, my name is Cooper Nicholson, and this is my Physics 2211 Lab 4 Oscillations Report. The purpose of this lab is to analyze the position of a single mass system oscillating in two dimensions and calculating the energy changes of the system. By the end of the lab, I could determine that the energy principle is satisfied, so the total energy change of the system is zero. One principle that we used is Newton's second law, which includes the momentum principle, which can be used to derive the position and velocity update formulas. We use Newton's second law here because we need to find the net force acting on an object by summing its forces from interactions with other objects. Another principle we use is the energy principle, which allows us to calculate the change in kinetic energy, gravitational potential energy, spring potential energy, and total energy. On this slide, I have listed out the general formulas for changes in these energies, but the initial and final conditions are still needed to find the changes in energy. I use the video provided to us, so my system is the mass, spring, and earth with nothing in the surroundings. This allows us to set the total change in energy to zero. For initial conditions, the mass of the object is 0.402 kilograms, the initial position is negative 0.122 meters, and negative 0.635 meters in the x and y positions respectively. The initial velocity is 0 meters per second, the magnitude of L is 0.7 meters, and L0 is 0.123 meters, and K is 6.83. You can see how I set up the coordinate system in Tracker and graphs of the data collected from Tracker on the right. For the computational model, I plugged in the initial conditions that were mentioned on the previous slide and used the formulas to find the kinetic, potential, and total energy. I also used Newton's second law to find F net equals the sum of the force of gravity and the spring. Then using the velocity update formula, I calculated the object's new velocity and then used that to find the ball's new position with the position update formula. Next, we updated the spring's position and stretch, and finally, we updated the new energies of the system. Here's the data from the computational model and the observed data on one graph. Notice how for the position graphs, the experiment roughly models the computational model. However, looking closely, we can see that as the experiment continues for more time, the graphs start to deviate. This suggests that in the real world, our experiment was not a true closed system as there were other forces present acting on the mass, such as drag, which was not accounted for. Another possible error source is human error when locating the center of mass of an object in Tracker. For our what does it mean question, we can see that the energy principle is satisfied because the change in energy is approximately zero throughout the entire time. Note that this means that the kinetic energy will cancel out with the gravitational energy and spring potential energy and the sum of the potential energies. For the next part of the what does it mean question, I found the oscillation period using x and y graphs by looking at the time intervals between the peaks of the data. Notice that the period of oscillation is slightly different depending on if you use x or y direction. This means that we will have lots of deviation since the period of oscillation is used to calculate the spring constant, which then affects the spring force, net force, and kinetic energy. In conclusion, we used Newton's second law and the energy principle to determine if the energy principle was satisfied in our experiment. We analyzed the position of the spring mass system oscillating in two dimensions and calculated the energy changes of the system. And we noticed that in the real world, systems may not be closed even if theoretically they are. Thank you.